Okay, we're now going to talk about problem 6, which is all asymptotic analysis. And so 6a says we have this function f1, and what happens is we initiate a random, and we get some number between 2 and n over 2. Then we have 2 for loops, and in the outer one, we're going to increment by 1 going up to n over d. And in the inner one, we increment by n over d going all the way up to n. And within the for loop, we do a constant amount of work by printing. And so the question is, what is the worst case cost of executing this function? And so let's think about it for a moment. D could be anything in some big range, but regardless, what's going to happen is that we have the outer loop, which is going to go n over d times. And then for every time the outer loop goes, the inner loop is going to happen. And it will happen. We're going to go all the way from 1 to n, and sort of the jumps we make are going to be of n over d in length. So in other words, the number of calls we do is n divided by n over d. Because again, we're going from 1 to n, which is sort of this top number. That's what we need to reach, and we're getting there in increments of n over d. And so the amount of sort of steps it takes to reach is n divided by n over d, or d, right? Because n divided by n and then the d moves on top. It's all math stuff. I'm not good at math, but that's what we get. And so basically the inner loop does d work. The outer loop happens n over d times. And so in total, outer times inner gives us n work. And so this is exactly what happens. And so this is one way to analyze this, right? We just said, okay, no matter what really ends up happening? We have this math that works out and we have n work. And so that's going to be option B. However, you might have done this a different way where you tried to see if there was a different worst and best case. And we can also look at that really quick. So sort of looking at the extreme options for what D could be, it's going to be somewhere between 2 and n over 2. So let's see what happens when D equals 2. Well, then we're just going to go in the outer loop from I equals 0 all the way up to I equals n over 2, right? And in the inner loop, we're going to start j at 0. We're going to go until j is less than n, and j increments by n over 2, right? And so how many times does this inner loop happen then? Well, j first equals 0, then j equals n over 2, and then j equals n, right? Because we're incrementing by this huge amount. So we're taking like giant steps, right? We just do it twice. And so this whole thing is really like constant work now because we're just going 1, 2, 3, 1, 2, 3. It's like a negligible amount of work. But the outer loop is going to go all the way up to n over 2. And so this is roughly linear. And so this is one way where we can analyze, oh, when d equals 2, we still have linear runtime. And let's look at the opposite case, right? Where d instead of being 2 is n over 2. Well, then the outer loop goes I is less than n divided by n over 2, right? Because we're looking at that case where d equals n over 2, I plus plus. And then we do j equals 0, j less than n, and then j plus equals n divided by n over 2. And so this really works out to I equals 0, I less than 2, I plus plus, right? That's what this works out to. And the inner loop is j equals 0, j less than n, j plus equals 2. And so now what happens? Well, the inner loop is essentially constant, linear, because we're going all the way up to n and we're just incrementing by 2 each time. But the outer loop is now constant. And so either way, it's going to be linear times constant in this extreme case, right, where d equals n over 2. And in the other case, it was also linear times constant, where d equals 2. And so we see that either way, we're getting a linear amount of work done. And so we know b is definitely one of the correct options, right? This function is in theta of n. And honestly, this is a little tricky, but one of these options is not like the others. Option I is actually using a big O bound, not a theta bound. And so what does that actually mean? Recall a theta bound means that omega and O are the same, and an O bound is just the upper limit. And so if our function C of n is in O of n, or O of n to the fourth, it means it's within the set of functions that are upper bounded by n to the fourth, right? And so n to the fourth is some really crazy fast growing function. I don't even know what it looks like, something like that, like something really crazy. And anything that can be bounded by this, or anything that could live below it, is going to be in that set of all functions, upper bounded, or in big O of n to the fourth. And so n, linear, is definitely going to grow slower than n to the fourth, or it's never going to go faster, so it's upper bounded by it, which means C of n belongs in this set. And that is 6a. Moving on to 6b. So now we have this function f2, and we're going to again look for the worst case cost. And so here, what happens? Well, we see the outer loop happens a linear amount of times for sure, right? Then the inner loop is going to go for 2 to the I amount of times, where I is the number of the outer loop. And so the way I would approach this is to sort of count out what the calls look like and see how this appears. And so we see, we start when I equals 0, how many times does the sort of inner loop run? Well, we're going to go until j is less than 2 to the 0, which is 1. And so all we do is look at j equals 0, right? What about when I equals 1? Then we're going to go until j is less than 2 to the 1, which is 2. So we look at j equals 0, j equals 1. When I equals 2, we go until 2 to the 2, or 2 squared, which is 4. And so we're seeing that the amount of work we do, or the amount of times we print, right, this inner loop runs, is going to be the same as this sort of upper limit. And so just doing this one more time, we see we now have 2 to the 3, which is 8. And we'll go 16 when I equals 4, right? 2 to the 4, and so on and so forth. And we won't end until I equals n, at which point we are going to do 2 to the n, right? And so this is the total amount of calls we are doing. I've sort of written it out, and we see the amount of work we're doing. We're doing 1 unit of work, then 2, 4, 8, 16, so on and so forth, until we reach 2 to the n. And so now the question is, what does this all sum up to, right? What does 1 plus 2 plus 4 plus 8 plus, and then 2 to the n add up to? And so you may recall, this is one of our sums that we've grown to love in this class, which says that in a geometric sum like this, the sum of all the work is just going to be this last term, 2 to the n. And this is because it's growing in a way where the last term sort of dominates, right? Like 2 to the n, if it looks like this, the term before it is much smaller in comparison, right? It's doubling each time, which means the last term, we can almost think of it as like dominating the sum in a way. I would say the actual math explanation for this is a little more complicated than we'll go into in this video, but hopefully you did recall this sum in general from when we've showed it other times in the class, and that's 2b. Then we have 2c, and so let's take a look at how this works. We have 2 for loops, and we see that basically the condition to break is just when I and j add up to n. And so just like earlier, I'm going to do an approach where I just draw out the series of calls and see what they look like. So when I equals 0, right, j, this inner for loop is going to have to go all the way until we reach the end, or when j, like we're never going to reach this, right, because j is initially 0, and 0 plus 0 is not n. 0 plus 1 is not n. And eventually j will equal n, but then we'll break from the inner for loop because we've broke this condition. Okay, what about when I equals 1? Well, then we're going to go all the way from j equals 0, and we'll finally break when j equals n minus 1, because n minus 1 plus 1 will indeed add up to n. Then here we're going to start there, and we'll go all the way up until n minus 2, right? And finally, sort of skipping ahead in time, when I equals n minus 1, we're only going to have to look at j equals 1, right? Because then I plus j, or n minus 1 plus 1, will add up to n. And so you basically see as we go on in time and I gets bigger, j doesn't have to grow as much. Cool. And so now the question is, how many times in total, like how much work is there? And so the way I'm going to measure this is sort of how many times we have to evaluate the inner loop, right, what's in here. And so first it's n times, then it's n minus 1, then n minus 2, and we keep going. And so in total, the work is 1 plus 2 plus 3 plus 4 plus n minus 2 plus n minus 1 plus n. And so again, this is one of those sums that you hopefully have learned throughout this class, which is that when we have this arithmetic sum where we're incrementing by a tiny bit each time, the total work is actually going to be n squared. And if we were to contrast this to the last one, where remember we saw that like when we have this geometric sum that's growing a lot, the last term is significantly larger, and so it sort of dominates. That's, I think, like the picturesque explanation for this math. The simple explanation here is that each time the amount is only growing by a tiny little bit, and so there's a lot more work, and so the last term is not really that much bigger than the term before it. And in total, this work kind of looks like n squared, right? It's a triangle. Yeah, that's another good visual actually, is that we have a triangle where we have n on one axis, right? The final term is that tall. And how many terms are there before it that are each a little smaller than it? Well, it's n because we go 1, 2, all the way to n. And so this triangle has an area of n squared. These are all different ways to sort of rationalize the sum, but the main thing is that hopefully you had this on your cheat sheet, right? And we recognize that when we see this pattern, the total work done is n squared. And so that's 6c. Now let's look at 6d, which talks about f4, this function. And so here we see what happens is that we have some sort of loop in the body, right? And that goes from 0 to n, does a linear amount of work. And then we have a recursive call that cuts the input size in half. And so first, let's just look at sort of the recursive call stack. We see that first we have a call that accepts an input of n. That has a child call, which has input size of n over 2, then n over 4. And we go on and on and on until eventually we reach, we're going to get down to like 0, basically. And note that this will work out because we're doing 4 division, right? So eventually we're going to reach that point when we get to the bottom. And so now these are the calls, and we need to figure out how much work gets done at each level or at each call. And as we saw, this is just a loop. It's linear. It's going all the way from 0 to n. And so we're getting a linear amount of work done at each of these levels, which means that the actual work getting done is the size of the input. And so this is I guess 0 work, and right above it, right, we would have like 1 or 2, depending on how the division works out. But regardless, then the total work done is just the sum of all the work done at every level, which is n plus n over 2 plus n over 4 plus da 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 da. And again, hopefully you're recognizing the sum, and this is the same geometric sum we saw earlier that adds up to a total of n. Cool, that's 6D. Now we're going to talk about 6E. And so this one, we start with a call to F5, and then we do recursive calls to some helper method named helper. And we're giving the runtime for F5. So assuming that we pass in initially n and 1, what happens? Well, if n is less than 0, we return, that's the recursive base case. Then we have some sort of loop, and I'm going to analyze the work for that later, but it's about linear in n times I. And then we have the recursive calls. And so this is what I want to look at. Let's sort of draw out the recursive call tree, right? So we start with a call that passes in n and 1. And this leads to a recursive call with n over 2 and 4. And this leads to a recursive call with n over 4 and 16. And so again, I is getting multiplied by 4 every single time. Or in other words, if we multiply by 4 repeatedly, right, that's just going to be 4 to some power. And the power is just sort of the level in the recursive tree we're at, or the height, right? And so if this is level k equals 0, then we see 4 to the 0 equals 1. And so that's here. 4 to the 1 equals 4. 4 squared equals 16. And so we're just repeatedly multiplying by 4 over and over and over. And that's how the second argument is growing. And the first argument is just getting halved each time, kind of like normal. And eventually we'll reach the point, the base case where n is 0, like 0. And what is this number, right? What's the second argument? Well, it's going to be 4 to the k, where k is the height of the tree, or the number of levels. And what's the height of this tree? Well, if we're repeatedly having n, and we only stop when n equals 0, or like reaches sort of gets so small that it's not there anymore, then the height of this is going to be log base 2 of n, because we're repeatedly having it. Hopefully this is a pattern you've seen before, but if you haven't, we'll explain really briefly. So we initially start with a value of n, and we have it at each level, right? So we multiply by half every single time we go down a level, which means repeatedly multiplying by 1/2 is just 1/2 to some power, where k is the number of levels. And we want to know what is k, or the number of levels, when n finally reaches the bottom. And so I know it says n 0, but when we're working with like log and multiplication, it's always easier to do 1. And we know that once we reach 1, 0 is just one step below that, right? Because when n equals 1, the recursive call below that will do 1 divided by 2, and that'll give us 0. So I'm just going to put 1 in there. And now let's solve this equation. And so we get n times 1 over 2 to the k, right? Because 1 to the k is just 1 equals 1. And then let's move this to the other side. So now we get n equals 2 to the k. And this just requires some math knowledge, but when you have something of this format, it can be rearranged to say log base 2 of n equals k. So all of this was just to figure out that the height of this sort of recursive stack is log n, which means k is log n. And so what we have here is 4 to the log n. Cool. So we did all of this, we've figured out the recursive calls, and now we need to know how much work gets done at each one. And the amount of work that gets done is going to be, in this for loop, which does amount of work linear to n times I, right? We're just looping up to that amount. And so at this call, the work done is n. At this one, it's n over 2 times 4, which is 2 to 2n. At this one, it's n over 4 times 16, which is 4n, and so on and so forth. And at the base, we don't really do any work, right? Because we enter this case. But we see that maybe like right before that, we had this level where we did roughly like approximately 1 times 4 to the log n work. And so all that's left to do is sum up the total amount of work done, right? And so we saw that we have n plus 2n plus 4n, all the way up to like approximately 4 to the log base 2 of n. And so this is a little tricky, it requires some math knowledge, but what I see here is that 4 is just 2 squared, right? So this is 2 squared to the log base 2 of n, which is really just the same as 2 to the log 2n. So we can switch the order here, right? That's just like a math thing. And we know that x to the log x base x of y, this whole thing is just equal to y, right? Because log and exponent are the inverse of each other, which means this whole thing is really just equal to n. And so we get here is n squared. So in other words, the total sum is n plus 2n plus 4n plus da 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 da, all the way up to n squared. And this again is just that geometric sum that we keep seeing, right? Where we are sort of going all the way up, doubling each time until we reach n squared. And if it helps you out, maybe another way we can look at this is that if we pull out the n, this is really just n times 1 plus 2 plus 4, all the way up to n, right? And this sum we are familiar with. We know that this one adds up to n. So in other words, we have n times n, which equals n squared. So the overall runtime for this is d, n squared. Great. Finally, we're going to look at f. And so this is another kind of tricky recursive one. And what we do is we have a recursive call, no matter what, on this line. And then if n divided by 3 equals n plus 2 over 3, we're going to result in 26 more recursive calls. And so this is an interesting sort of question. And so it makes me wonder, where is this case true? And so remember, Java does floor division, right? So things that have a remainder will still also are going to be like sort of chopped off, right? And so it's possible that two numbers, even though they're different, when divided by 3, result in the same result because the remainder doesn't matter here. And so when specifically would this happen? Well, if n is divisible by 3, right? Then let's take an example. Let's say n is 9. 9 divided by 3 is 3 with the remainder 0. But n plus 2, 11 divided by 3 is also 3 with the remainder of 2, right? And so we see, we're basically, it almost reminds me of hashing, right? Where we're seeing like what kind of things like fall into the same bucket almost. And it's only possible when n is divisible by 3, because then if you add 2, you're sort of barely at the end of things that fall into the same like bucket or have a like the same value and just a different remainder. And so it only works when things are divisible by 3. And now knowing that, let's sort of look at these recursive calls. And so we see first we're going to start with n, then we do n minus 1, n minus 2, right? N minus 3. And at some point in here, right, n must be divisible by 3 because every 3 numbers were divisible by 3, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Like every 3 numbers, if we just keep incrementing by 1 or decrementing by 1, we're going to hit something that's divisible by 3. And so one of these calls, let's just say, for example, like this one, is going to end up leading to 26 more calls. And so we get 27 total calls, right? Because it's this one plus the 26 recursive calls that happen here. Like every 3 times, or in other words, n over 3 of the levels result in 27 calls. And so if we want to know sort of how big is this last level, well, that's going to be 27 to the n over 3 power. Because, again, 1/3 of the time, or n over 3 times, like n over 3 times, we end up branching 27 times, and that's ultimately the driving factor for how big this bottom level is. And because we're doing another, you guessed it, geometric sum, it's this last term or the last level of the tree that really determines how much work's happening, right? We're growing by a really significant factor. And so this last level is sort of dominating. And so this number is how big that last level is. And if we work it out, we see this is 27 to the 1/3 power times n. And the cube root of 27 is 3. So this is just 3 to the n. Thus, the correct option is G. And that is all of problem 6.